Hi everyone, it's Caelan from Kite, the AI-powered autocomplete and coding assistant. And in this video, we're going to be using Python to make a visualization of a virus spreading. Considering everything going on right now with the coronavirus pandemic, we want to use programming as a way to dig into what factors can make a virus like COVID-19 so deadly. Many outlets are creating informative graphs and visualizations right now using data science, and we were particularly inspired by the one in the Washington Post. We definitely recommend you check that out, and the link's in the description below. Today, we'll walk through how to build and run this data visualization using the most current statistics on the coronavirus. We'll be coding in Python using NumPy and Matplotlib, and all of our code will go into a file called virus.py. A link to the completed project repo is in the description of this video, so definitely check that out and follow along. Our hope is that by watching this video, you'll learn something about programming and pandemics. With that, let's get started. So let's start off by importing all the libraries and data that we'll need today. First, we import matplotlib.pyplot as PLT and matplotlib.animation as ANI. It's nice that Kite gives us some completions there. We'll be using these for our data visualization. We then import NumPy as NP, and that's what we'll need for some mathematical functions on the arrays. Let's also create RGB tuples to represent the colors we'll use to encode health status as uninfected, infected, recovered, and unfortunately dead. We'll use a dictionary to hold information specific to COVID-19. This will make it so that we can easily repurpose our animation for other contagious diseases by passing in a different dictionary with the relevant information. In fact, we'll have a video comparing COVID to other contagious diseases, so make sure to subscribe to our channel so you don't miss that. First, we create a virus class, which will hold all of our functionality. The constructor for our class will take one argument, params, which will be a dictionary with information about the virus in question, such as its basic reproduction number, its incubation period, and the distribution of mild and severe cases. This is among many other parameters as well, so we'll cover this more in detail later. Next, let's make our plot. We're going to use a polar plot, which has a circular graph that allows our visualization to show the virus spreading from the center outwards. This is like plotting points on a coordinate plane, but instead of using x and y coordinates to specify any point, we use the theta or r coordinate pairs to specify points within a unit circle, where theta corresponds to the angle in radians above the positive x-axis and r corresponds to the distance from the origin. First, we create an empty Matplotlib figure. Then we instantiate a polar plot by calling add subplot with 111 and projection equals polar. The 111 just means a 1-by-1 grid using the first subplot. This function call returns on axes object. Let's modify the axes to remove the grid lines and the tick marks. Let's then set the radius of our plot to 1 by calling setYlim 0, 1. Next, we create our annotations, which display the needed text that gets updated throughout the program's duration. Let's first create the day text, which we do by calling self.axes.annotate. Let's display day 0 centered at the top of our plot. This corresponds to a theta value of pi over 2, which specifies the y-axis, and an r value of 1, which specifies the top of our unit circle. We set the horizontal alignment to center and the vertical alignment to bottom. It may seem counterintuitive that we place text at the top of our plot by specifying vertical alignment as bottom, but this means that the bottom of our text will align with the point we specified, thus placing the text above our plot as desired. Then let's create 3 annotations below our plot to display the number of infected people, the number of deaths, and the number of people who have recovered. We create these the same way as the day annotation, but alter the values to position it at the bottom. Let's make the text color of each of these category annotations correspond with the node colors in our animation. Now we create the member variables that we'll be updating throughout our calculations. We need the day, number infected, number recovered, and number of deaths, all initialized to 0. We create 2 variables to track the number of infections, one to track the current number of infections, which we'll use for the infected annotation, and one to track the total number of infections, which we'll use in various ways, such as the logic for stopping the simulation. Next, we store values from our input params dictionary in variables. The basic reproduction number, denoted R0, is a measure of the contagiousness of a disease. So that means it represents the expected number of cases directly generated by a single infection in a hypothetical population that is entirely susceptible to the disease. We also store values for the rates of mild cases, severe cases, and fatalities, as well as the serial interval, which is the average time between successive cases in a chain transmission. For each infected person, there is some amount of time between the emergence of symptoms and the outcome of the disease, whether they recover or whether they die. This interval depends on the severity of the symptoms and tends to be longer for those who ultimately die. The various ranges represented as days are stored in params. We add these ranges to the virus's incubation period to reflect the entire interval of the disease, from infection to recovery or death. Here we can see there are 3 different durations for this virus. Those with mild symptoms will ultimately recover, and the time it takes to do so is represented on the low end as mild fast and on the high end as mild slow. Those with severe symptoms who ultimately recover will do so within the interval bound by severe fast and severe slow. And those with severe symptoms who ultimately succumb to the disease will do so within the interval bound by death fast and death slow. Now let's create a dictionary called mild to track our mild cases over the next year. Hopefully our pandemic won't last that long, and our simulations suggest that it won't, but we're just using a year as the upper bound of our time frame here. In the mild dictionary, the keys signify the recovery time in days for infected people with mild symptoms, ranging from mild fast to 365. The value of each key is another dictionary with 2 key value pairs, one for thetas and another for r's. Both of these values are initialized to empty lists, but they will get populated with theta and r values that, when taken together, specify the individuals with mild symptoms that recover on that given day. This means the xth element of the theta list combined with the xth element of the r list specifies a point on our plot that gets updated to recovered. Let's now create a severe dictionary, which will have 2 keys, recovery and death. Here we take the same approach to complete the severe dictionary as we just did with the mild dictionary. For our last addition to the constructor, we need to put restrictions on the extent to which our virus can spread on a given wave. Since a single infected person would not come into contact with an entire population of 4,500 people in one single day, we need to restrict the potential spread of the virus to just a subset of this population. We do this by creating 2 member variables, exposed before and exposed after, initialized to 0 and 1 respectively. Exposed before represents the amount of people that have been exposed to the virus already, and exposed after represents the total number of people who will be exposed to the virus by the end of the current wave. The effect of all this is that our virus will spread in waves, from the center outward, to a subset of our population. Now we create a function called initial population that initializes our plot with a population of 4,500. Let's set num currently infected and total num infected to 1, representing patient 0. We need 2 lists, self.thetas and self.rs, which we'll use to plot points in our visualization and to keep track of each person in our population. These are just like the lists we created for mild, severe, and fatal cases, but they represent the whole population rather than a particular segment. These 2 lists will comprise our 4,500 data points, each defined by a theta-r coordinate pair. Let's do this using the golden spiral method explained on Stack Overflow by C.R. Drost, and the link to that thread is available in the description below here. So now we have all of our 4,500 data points. Let's use the scatter function to plot them, making the size of the points 5 and the color gray. Then let's update the color of patient 0's point to red for infected. We'll call scatter on the first data point in our 2 arrays, which is at the center of our plot. Let's give patient 0 mild symptoms with the quickest recovery, so we append the 0th data point in our mild dictionary at mild fast. Now let's make sure to call initial population to back up in our constructor. Let's run our code and take a look at what we've got. we create a temporary instance of our virus class with the COVID-19 parameters and call plt.show. Right now, we're just looking at a snapshot of our simulation to check that everything is working as expected, and soon we'll be able to run the whole simulation from a main function. Before we get into the main part of the simulation, let's take a quick break so I can tell you how to code this faster with Kite, the AI coding assistant that I'm using in this video. Whether you're new to Python or already a pro, you should try out Kite as your autocomplete to reduce your keystrokes and save time programming. Kite is a free plugin for your code editor that uses machine learning to save you keystrokes while you're programming. So if you're using Atom, VS Code, Spider, PyCharm, Sublime, or Vim, Kite will seamlessly integrate into your coding workflow. Kite can complete entire lines of code, and it has a feature called intelligent snippets that will help you fill in arguments and method calls with variables defined earlier in your script. The window on the right side of my screen here is also a Kite feature called the Kite Copilot. It automatically shows you relevant Python documentation while you type based on your cursor location. This saves you time from having to Google search for docs. The best part of Kite is that it's free and you can download it from the link in the description below. Alright, now let's get back to our code. Next, let's create a function spreadVirus that calculates the number of newly infected people using a serial interval of 7 days. Remember that we're spreading the virus in waves. The number of people exposed in a given wave is the difference between exposed before and exposed after. So at the beginning of a given wave, we set exposed before to the value of exposed after of the last wave that we saw. And we check whether the current day is a multiple of our serial interval and whether our exposed population is less than our total population of 4,500. If day is a multiple of our serial interval, then we know to spread the disease. And if the number of exposed people equals our total population, then we know there is no one left to infect. So inside our conditional, we calculate the number of newly infected people by multiplying the R0 value by the number of people who are already infected, then round to the nearest whole number. We store this as the variable num_new_infected. Since not everyone who is exposed to the virus ultimately contracts the disease, we need to increment exposed after by 1.1 times num_new_infected, meaning 10% of our population is not susceptible to the contagion. For the last wave, we need to ensure that our process of assigning exposure doesn't surpass our total population of 4,500. So when exposed after is greater than 4,500, that is, when the logic of our expanding waves overshoots our population limit, we subtract exposed before from 4,500 and multiply the result by 0.9 to obtain num_new_infected. Then we set exposed after to 4,500. After this conditional, we add num_new_infected to num_currently_infected and to total num_infected. Now we randomly select our newly infected people. Let's call mp.random.choice, and we can look to our Kite Copilot for reference on its arguments. Let's pass in the range from exposed before to exposed after, new num_infected, and replace equals false so that it doesn't give us the same values multiple times. Then we use self.thetas and self.rs with new infected indices and list comprehensions to get the theta and r values for these indices. After this conditional block, we increment day by 1. After identifying our newly infected people, we have to assign them symptoms. So that means mild or severe, and that will determine how long the disease will last for them. Let's create a function, assign_symptoms, where we calculate the number of mild cases and severe cases in this new wave of people using the information stored in params. We randomly choose a set of indices from new infected indices that gets assigned mild symptoms using mp.randomChoice and call this mild indices. We then use list comprehension to get the remaining indices by finding the set difference between new infected indices and mild indices. To calculate the percentage of severe cases that recovered, we use 1 minus the fatality rate divided by the percentage of severe cases. We use this value to sort our severe cases into two groups: severe cases that end in recovery and those that unfortunately don't. Let's create two empty lists called severe indices and death indices. If there are any severe cases in a given wave, as revealed in remaining indices. We use the percentage we just calculated to sort severe cases in the correct proportion to our two new lists, severe indices and death indices. This is done the same way as we did with mild indices, with a NumPy random choice function and list comprehension. Now that we've randomly assigned data points with symptoms and outcomes, it's time to assign the exact day each case will reach its outcome. Let's start with mild cases. First, we calculate the lower and upper bound for the day of their recovery. We do this by adding self.day to self.mildFast for the low end of our range, and adding self.day to self.mildslow for the high end. Then we loop over mild indices, and for each iteration, randomly choose a recovery day within this range using NumPy random randint. We then retrieve the theta and r values of this particular data point using the index with self.thetas and self.rs of our total population. Finally, we update our self.mild dictionary with this information. For the key that corresponds to the recovery day in question, we append the theta and r coordinates to the lists that are sorted as values to their respective keys. We use the same logic to determine the duration of severe cases that end in recovery and severe cases that unfortunately don't. That's it for this function, so let's just make sure to call it back up in spread virus. Next, we make a function called updateStatus that will update the color of plot points when a recovery or death occurs. Let's first do the mild cases. We retrieve the lists of theta r coordinates from the mild dictionary for the current day, which represents those with mild symptoms who recover today. Then we pass these lists to the scatter function and set the color to green to denote recovery. After that, we add the number of recovered patients, which we can get by taking the length of either list, and we add that to self.numRecovered. We then subtract this number from self.num currently infected. Now we do the same thing for people with severe cases that end in recovery, and likewise color them green. And finally, we do the same thing for people with severe cases that end in death, but we set the color of these data points to black. Now let's return to spread virus function and call updateStatus right after we increment self.day. Along with updating the color of our plot points, we need to update the annotations that we created in our constructor. So let's create a function called updateText. For this, we use the function setText on each of our text member variables, which track the day as well as the amount of infections, recoveries, and deaths. Let's begin with the day variable. We set the text of the day variable by calling self.dayText.setText. We pass in the string day formatted to be concatenated with self.day, which is the dynamic part of this text variable that increments with each passing day. We set the infected text variable in the same way. We call self.infectedText.setText and pass in the string infected formatted to be concatenated with self.num currently infected. Same with the deaths text variable. We pass the string deaths formatted to be concatenated with self.numDeaths and into self.deathsText.setText. And again, same with the recovery text variable. We pass the string recovered formatted to be concatenated with self.numRecovered into self.recoveredText.setText. That's it for this function, so let's return to spread virus and call it right after updateStatus. And now we get to start the star of the show, Matplotlib's animate class. Particularly, we're going to use the function funcAnimation. The animation shows our plot to update continuously while the program is running. So let's create a function called animate for this. We create an animation called self.anim by calling ani.funcAnimation and passing it to our figure, the spread virus function, the keyword argument frames with no value for now, and repeat equals true. If we look over at the Kite Copilot's documentation for funcAnimation and scroll down, we see that frames can be a generator, an iterable, or a number of frames. The value we pass for frames determines the iteration in which we terminate the repeated calls to spread virus. So let's create a function called gen for generator, which we will pass to frames in our animation. We know that the virus has run its course once every infected person has either recovered or died from it. So let's say while self.num's deaths plus self.num recovered is less than self.totalNum infected, yield. Then we return to our func animation call and set frames equal to self.gen. So we have our animation that will repeatedly call spread virus until every infecting case has reached its outcome. In each wave, we update the color of points for new cases of infection and existing ones that have reached an outcome. We'll implement one more animation so that the new case statuses of a new wave get updated gradually, which is more aesthetically pleasing rather than appearing all at once. Let's go back up to spread virus. We left off by making lists of the thetas and r's for all the newly infected data points on a given day. We're going to make another animation to make our plot points get updated in a more appealing way. These animations run in separate threads, which means our other animation for spread virus will keep running until we pause it. We pause it by calling self.anim.eventSource.stop. We'll need two functions to get this visual effect. The first is our function for plotting points individually, which we call one by one. It takes several parameters, I, thetas, r's, and color. Then we call self.axes.scatter and pass the thetas at I, r's at I, set the size equal to 5, and the color equals color. The other one is a generator function called chunks. This divides a given list into chunks of equal size. We need this function because some waves are too large to plot point by point. It'd take forever, so we're going to plot them by chunk and chunk instead. We do this with a for loop over the range of our population, yielding each chunk from I to I plus n. Let's return to spread virus. We create a conditional that determines how we want to animate based on how many points we need to plot. For our if statement, let's say that if the length of new infected indices is greater than 24, create a variable called sizeList. That's the length divided by 24, rounded to the nearest integer. Feel free to play around with this value. We decided to use 24 as our threshold because that makes the updates to our animations nice and smooth. Let's then create theta chunks using our chunk function, passing it thetas and sizeList and casting the result to a list. Let's do the same for the R chunks. Now it's time for the animation. Let's call this one self.anim2 and once again call Annie.funcAnimation with our figure and this time passing it one by one with the following arguments. Interval equals 50, and this means 50 milliseconds between each frame. Frames equals the length of theta chunks, and fargs equals theta chunks, R chunks, and red. In our else statement, which runs the length of the new infected indices is less than 24, we do the same as our if statement, except we set frames to length of thetas and fargs as thetas, r's, and red. Now all we need to do is pause anim2 when we call 1-to-1 and resume anim. Let's go back to the 1-to-1 function. And let's add a condition that once we've plotted all the points in a given wave, we stop anim2 and we start anim. The last step of our project is creating a main function. We create a coronavirus instance of virus by passing it COVID-19 params defined at the top of our file. Then we call coronavirus.animate to start our animation and plot.show to display our plot. Finally, we can add this code fragment so our program runs directly from the command line. And we're finally done. Let's run our coronavirus simulation.
that's how to make a visualization of a virus spreading using Python. I don't know about you, but for me, after digging through all this data, it's definitely a bit scary taking a look at how quickly and vastly a virus like this can spread. So it's important that we really take that into consideration and we respect what our governments locally or nationally are advising to slow this contagion. All in all, from all of us at Kite, we wish you good health and safety, so please be careful and smart. Thank you for taking the time to watch this video. Hopefully it's helped you learn a lot about Python and especially about pandemics. Again, check out the link in the description below for the GitHub repo. Hope you get that running and check it out even further if you haven't yet already. In an upcoming video, we'll run this simulation on a handful more of well-known epidemics that we've seen in the past. So make sure to subscribe to our channel so you don't miss it. Also, make sure to download Kite because you'll code faster and smarter. And finally, thanks for watching. See you on the next video.